Hello everyone, Assalamu alaikum. Welcome back for another video in the series of VLSI systems. In this video, we are going to discuss about how to design basic logic gates using pass transistors. We will start off with our design of multiplexers because we know that a multiplexer can be used to design different logic gates. Keeping multiplexer as a base design, we can design all the logic functions accordingly. So in 2 cross 1 multiplexer, whenever the selection line is equal to logic 0 and this first input will get connected to the output. Similarly, when the selection input is equal to logic 1, then the second input will get connected to the output line. That means that at any given time, only one of the input will be active. So first, let us see how to design a multiplexer circuit using this pass transistor logic. This is the circuit of 2 cross 1 multiplexer using pass transistor logic. As you can see over here, this control input S and S bar are connected to the gate input of the pass transistors, and here this D0 and D1 are the two inputs of multiplexer. So whenever this S is equal to 0, then S bar will be 1. This means that in this condition, this first transistor will be in the on condition while the second transistor will be in the off condition. Therefore, this D0 output will get connected to the output node. Similarly, when this S is equal to 1, then this S bar will be equal to 0. So in this condition, this first transistor will remain in off condition while the second transistor will remain in the on condition. And in this case, this D1 input will get connected to the output node. So in this way, we can design this 2 cross 1 multiplexer with the help of pass transistors. Similarly, we can also design 4 cross 1 multiplexer. As you know, in the 4 cross 1 multiplexer, we have total 2 selection lines, that is S0 and S1. And as you know, for 2 selection inputs, we have total of 4 different input combinations. So here for the input combination, the 2 transistors are connected in the series combination, and this D0, D1, D2 and D3 are connected to the edge input line. So whenever both S0 and S1 are 0, then the first two transistors will be in the on condition, and in that case D0 line will get connected to the output node. And similarly, for the different input combinations of this control inputs, only specific line will get connected to the output node. Now, if you see over here, these two transistors are connected to the one end of the S1 bar. Similarly, over here, these two transistors are connected to one end of this S1 transistor. So instead of using two separate transistors, we can use only single transistor. So this is the simplified circuit of the 4 cross 1 multiplexer. And as you know, using the multiplexer, it is possible to implement any Boolean function or logic gate with n plus 1 variables. That means here we can also implement any two input logic gate just by using 2 cross 1 multiplexer. So let's do that. First, let's consider a two input AND gate. The logic equation for a two input AND gate is A dot V. Comparing this to the logic equation of a 2 cross 1 mux, we have only one product term and there is no sum term. Let's consider the truth table of an AND gate. So we know that all the input combinations generate 0 except for the last one, which is if both the inputs A and B are 1, then only the output will be 1. As we have seen in the 2 cross 1 mux, we considered the selection line to be the input to gates. So whenever we will design a circuit using pass transistor, we will consider one input to be equivalent of a selection line. So in this case, we can consider A as a selection line. So as you can see, we can combine these two inputs when A is 0 and these two inputs when A is 1. So this is the circuit that represents an AND gate. Now let's see how it is made. For first pair of inputs, when A is 0, that means it is represented by A prime. We can see that output is also 0. So considering this A prime, so its input should be 0. Similarly, for A to be 1, this is represented with this A signal at the gate of a transistor. The output is equal to B. Combining these two, we can form an AND gate, like so. As you can see, once again, A is 0, which is represented by this input to NMOS and the output being replicated at the input side. Similarly, for A is equal to 1, which is represented by this B output is represented by equivalent to B. So we give an input of B here. This constitutes our AND gate. Now let's quickly discuss about OR gate. An OR gate has an output equation A plus B. So comparing it with the equivalent circuit of a 2x1 mux, we have the same circuit. But what about the inputs? Pass transistor circuit for OR gate is represented on the right hand side. Considering the truth table, we have all the input combination generates an output of 1 except for the first input in which both A and B are 0. Then only the output is 0. We can take one input as a gate signal and the other as an input signal. So if we take A as a gate signal, then we can see clearly for A is equal to 0 or A prime, the output generated is B. So this is A bar, the input being B. So that will mean whenever this transistor is turned on, the signal passed will be B, whether it is 0 or 1. And when A is equal to 1, this logic is represented here. The output is 1 no matter what. So this can be represented by VDD signal, which is represented here. So combining these two, we form an OR gate. Next we have a NAND gate. For a NAND gate, the logic equation is y is equal to a dot b whole bar. And looking at the truth table, all the input combinations generate 1 except for the last one, in which for which both inputs are 1, only then the output will be 0. So this is the equivalent circuit for a NAND gate. Now let's understand how this is made. Again, we have to consider one input being at the gate. So taking A as input on the gate, we have A for A is equal to 0 or A bar, the output is 1. So its input is considered as 1. Similarly, for A is equal to 1, the output is B bar, the opposite of B. So the input given to this gate will be B bar. So whenever this transistor is turns on, it will pass the opposite input that is given to B. So in this way we can make an AND gate. Next, consider an OR gate. For an OR gate, the logic equation is y is equal to a plus b whole bar. For NOR gate, only first input combination, that is A being 0 and B being 0, generates a logic of 1, and all the other combination generates 0. For this, again, we can make one input as our gate signal. So let's try to switch it up. If we consider B as a gate signal, then from the truth table, you can see when B is equal to 0, that is this B bar signal. The output generated is the inverted signal of A, that is A bar. So this is represented by this combination, and whenever B is 1, that is B, the output generated is 0. So we can give a 0 here. So combining these two in this way, we can make a NOR gate. Similarly, let's consider an XOR gate. For XOR gate, y is equal to a dot b bar plus a bar dot b. For an XOR gate, we know that if both the inputs are same, then it generates 0, otherwise it generates a 1. So considering this, again, let's consider one input as a gate signal and the other input will be fed to the input of the transistor. So considering A as an input fed to the gate, for A is equal to 0, the output generated is exactly equal to B. So for A0, A bar input is given as B. Similarly, for A is equal to 1 or A, the output generated is the inverse of B. So input given here will be B bar. So combining these two, we can make an exclusive OR gate. And in last example, let's consider an XNOR gate. For an XNOR gate, the logic equation is y is equal to a dot b bar plus a dot b. And for XNOR gate, we know that if both the input combinations are same, then output will be 1, otherwise output will be 0. So constructing this gate, taking one input signal as a reference signal to the gate and the other one being fed to the input. In this case, again, let's consider A being fed to the gate signal. So for the first two combinations, A is equal to 0, that is represented by A bar. The output is the inverse of B, which is represented here. And for A is equal to 1, the output is same as B, which is represented here. So this constitutes our XNOR gate. And this completes our discussion on the construction of logic gates using pass transistor logic. I hope this video was helpful. If you have any questions, leave them in the comment box below, and I'll see you in the next video.